No, I thought it would be.
Excellent. Hello everyone, good afternoon, and thank you for coming to this session. As you know, we have a lovely guest speaker today coming from the US, Mr. Francisco Castano, who is the founder of Geometrica about 30 years ago. They have done a number of projects all over the world, and you are going to learn more about those projects. Thank you very much for joining us. It's a great pleasure to have you. And the relation between the Spatial Structures Research Center of the University of Surrey and the company, in particular Castano family, goes back for 4 decades. So his father received a prestigious award from the Spatial Structures Research Center, which is called Pioneers Award. This is a specific award to recognize the great contribution to the design and construction of these specific types of structures, and based on his contribution to the field, he was recognized as one of the Pioneers Award winners. So it's a great pleasure to have you. Thank you very much for joining us today. And we are going to listen to his presentation, and you will have a chance to discuss your questions or any point that raised. So over to you, Pancho. Thank you.
Thank you, Professor Beneja. And thanks everyone for being here, for inviting me here. It's a great honor for me to be here. As Professor Beneja just said, my father was here not only 40 years ago, that was when the awards, and he was recognized with that, which is very nice of the university, but also 9 years before and 18 years before. I think he was here in 1966 for the first conference, and presented a paper at the time. So yeah, we go way back. I was a little kid at that time, but had the opportunity to see the research that you all were doing here back when I was a child, and inspired me to go into this field along with my father's work. So here we are, almost 60 years later, still at it. So I'm going to talk about more recent stuff. Stuff we'll be doing at Geometrica in different parts of the world with types of structures that you all have a research center for. We used to call them space structures. I don't know, that got confused because space structures, outer space, so we call them spatial structures right now. We use still space structures often. Geometrica has a kind of a unique connector. It's an aluminum hub, it's an extrusion, and it's cut to length as you would cut chorizo. It's just a cylindrical hub with slots, and the tubes are, we call them coined. They are flattened to match the slots on the connector. This is a very efficient connector that is very easy to put together, as you will see here. The tubes are inserted into the slot and tapped with what we call a digital assembly tool, better known as a mallet. So you are able to assemble these sub-assemblies and then join them together to build the structure. The trick, though, is that the tubes carry the information and the parameters that make possible to give curvatures. So we have what we call coining angles at the end of the tube that provide for curvature in the direction of the tube. But we also have the twist. And if you look at the tube on end, as you can see in the drawing, one of the flattened ends has an angle with respect to the other. And that provides for variation in the curvature. So you can have doubly curved surfaces with different curvatures in different directions. We can do single layer because the joint that you saw is capable of transferring moments across it in the strong direction. There's also a weak direction where we don't transfer moments, but generally the structures are triangulated in that direction, so you don't need to carry moments in that direction. However, in the strong direction, so to call it, we are able to do single layer structures or do what we call barandeel structures, where two layers are joined with posts. Since you have curvatures, there's very little shears transferred. And most of the work is done in a membrane action. So that's why we are able to do these single layer and geodesic structures. However, for very long spans, you still need sometimes to go with double layer or with reinforced ribs. And all those geometries are possible with this joint. The thing about the joint is that it's as strong as the base tube that you're joining. Usually, I mean, almost always we get a failure in the tube by yielding before we get failure in the joint. So even in the case of the left coupon that you see in the screen, the tube is already stretched. So we already had a yield failure before the joint broke. And in some cases, maybe 10% of the cases, we actually get the failure away from the joint, as you see in the right coupon. So that one is the structural part of the system. However, there's a whole other world of important building components that are called cladding. And most people miss how important this is. And the importance is given to the structure part, but the cladding is probably more important. And so how do you fix cladding onto a structure that has these weird flared out tubes at the end? Well, we put what we call a purlin, and this is the simplest of those cases. The purlin is just a formed tube. The bottom is curved like the tube, and the top is flat. And it provides a spacer between the space frame and the cladding. So with this simple purlin, you can attach metal deck, corrugated metal deck. You can also attach it on the underside of the structure to provide for interior cladding. Interior cladding is useful when you want to show off the structure, which happens often enough, but also when you want to prevent, say, combustible dust from accumulating on the structure and creating an explosion hazard. Or corrosive materials that you want to store. So we put plastics, as in this case, to protect the structure from these corrosive elements. With the simple purlin, you can put standing seam. Standing seam roof is a very efficient way of making sure that your structure is completely waterproof. And it can be adapted to curved surfaces, like you see in this picture. We use wood deck in some cases, and you can put deck made out of, many other materials, but just to give you a few examples. So the simple purlin provides for many solutions, but not all. For instance, it's not a great solution for attaching glass, which is another of the types of products that we get asked to do all the time. So we get into more elaborate purlins. And this, for example, is a hierarchical gutter system where we have a three-way grid of gutters that drain through the continuous rubber gutter that goes all the way from the water break to the edge of the dome. And we can, in this way, clad all kinds of buildings. Here's how it looks from the inside. The purlin sits on top of the space frame, and then it carries the glass and can cover, say, dinosaurs or whatever, so this is another different type of purlin, but we have many others. This, for example, is a type of system for facades, and we can capture positively a cassette of glass or stone or anything else to do vertical or even hanging cladding. Here, for example, is acid etch glass on a vertical facade, and this is another vertical facade with stone supported from the space frame. So as you can see, there's just tons of different complementary systems to the structure. The structure is important, yes, and it's guiding or determining for the cost of a building. But it's definitely not the only thing, and particularly when you're working with architects, they want to do weird stuff, as some of you might be right now. And so we need to come up with these complementary solutions for giving them what they need. Oh, one more I haven't shown you. This is for fabric. We also do quite a lot of structures clad with fabric. And for that case, we don't really use a purlin. We use a purlin stool, sort of. We use a plate on top of the joint, and then the fabric, maybe a single sheet or maybe patches that are then joined, and we can put fabric over a dome, and it looks like this. Lets the light through, or doesn't. You can put complete blackout fabric, or you can put transparent fabric. So with these types of solutions, the structural solution, the cladding solution, we're able to do many different types of projects. I want to show you some examples of industrial and agricultural projects. As you may know, in industry and agriculture, it's not how beautiful the building is, but how inexpensive it is. And we are competing with conventional structural systems, but giving a client a low-cost solution, otherwise they would not buy it. So we have these examples where all they're doing is storing dirt. It's sometimes a little more than dirt. This probably is some kind of copper ore, meaning that eventually they will extract up copper from some production process like leaching, or they process this dirt and turn it into metal. But they have to store it somewhere, and this provides for inexpensive storage. In this particular case, it's probably a 100-meter dome. Sorry. Meter dome, and again, we compete with conventional building solutions. This is an aircraft hangar. Again, it's a space frame, simple space frame. This one is in Arizona, and it was a competitive solution compared to conventional metal joist buildings or structural systems. But the trick is, there are many products out there for buildings that are up to, say, 30-meter span. When you get past that, then it always requires a structural engineer, because there aren't that many cookie cutter solutions already done. So you end up hiring a structural engineer who will design a custom structure, and you will get something like this. In our case, we skip that one step. So often we end up competing with structural engineers. The client calls us up, can you do a space frame? Yes, sir, it will cost you so much. While if they go the conventional route, they have to go to the structural engineer, design a structure, pay a fee, and then set that out for competition. So we can have a bit of a shortcut trying to get to a solution that is quicker, faster, and often low cost. This, for example, is another set of buildings in Taiwan. Each of these stores 180,000 tons of coal. They are in Xinta, near Kaohsiung City in Taiwan. And they're designed for wind loads of up to 250 miles per hour. Some ridiculous amount that will never happen in the whole world, but the particulars of this project were very interesting, and the client needed a dome with a tremendous wind load capacity. So that's what they are. We do long span space frames. I think this one was in the order of 35 or 40 meters, don't remember exactly, but for a cement plant, and they do all the palletizing and packaging inside it. This two are 113 meter diameter. They are in South Africa, and they were built back in mid-2000s. in Lichtenberg. We also do grain storage. This is what we call the agri-dome. And we are able to store a huge amount of grain for less money than it would cost to build the conventional silos that you see in the photo to the right. The advantage of this is that you can have excess production because you never know how much tonnage you're going to get out of your crop. So with these large storages, you can have excess capacity storage and sell the grain when it's more convenient to you, the producer, rather than when there's bad weather and you have to just give it away. This is the inside of the grain storage. Again, a product that doesn't need to be expensive, quite the contrary. It's sold on the benefits of giving a low-cost product, including supply and installation. And most interesting, we store not only grain, not only dirt, but also water. So we've done some water tanks, particularly in Mexico. And you can see that the space frame is used here not as a structural component in the end building, but rather as formwork. The space frame actually supports first a layer of thin steel, perhaps 1 centimeter, 3/8 of an inch thick, and that is set with studs perpendicular to the surface, onto which we put a mesh of reinforcing steel, and then we pour concrete in it. And it's a composite water tower that again is sold on its low-cost properties. This is another example of coal storage, this one in Florida. We did two 122-meter domes in Jacksonville. This project is in Bolivia. It's a 143 mining dome. It again stores the copper ore, maybe in this case zinc, I'm not 100% sure, but it stores it very inexpensively compared to other solutions. But one thing to notice is that the shape of the dome is not precisely a spherical dome. It has a odd bite there, and the reason for that is that this was a retrofit. In many mines around the world, governments and neighbors are requiring these mines to cover their existing stockpiles because they pollute the neighbors, and people don't like to eat copper dust in their soup. So they're being forced to do this, and we have to adapt to whatever boundary the particular stockyard has. So here we have this weird shape at the bottom, and we do that more often than is probably seen in the photos. But it's a requirement, and one thing that we, with this structural system, can do relatively inexpensive compared to conventional systems where everything is standardized or the same. This project is 145-meter diameter, probably one of the largest storage domes in the world. It's 94 meters tall. The actual Statue of Liberty that we have in New York, raising her arm all the way up, doesn't touch the apex of this dome if it was underneath, even standing on her pedestal. So it's a fairly big dome, 145 meters. You could actually put more than a soccer field in there with bleachers and all. But again, it's used for storing mineral ore. The reason it's so high is to shed snow, because there is 800 kilos per square meter of ground snow load on this dome. So you could actually park a couple of 747s on top of the dome and it would be okay. We did have to put that load at the apex, but at a certain point it just slides. And so when it was finished, it ran on the front page of the newspaper in Santiago, Chile. It says, "A new peak races in the Andes." another one in Chile. We did this 2 domes for cold storage, and here's the illustration of what I was telling you before, that we can adapt to whatever shape the client has for their stockyards. So they already had the stockpiles of coal, and you know, couldn't really fit a circular dome on these. So the client required that we do them in these odd shapes, and it was not an expensive proposition. They wouldn't have done it if it had been expensive. We were able to provide them with custom solution, bespoke solution. Turned out to be quite effective. Each of these is about 23,000 square meters coverage. The left one spans 207 meters in the longer direction and 150 in the shorter direction. And the other one spans about 180 in both directions, meters. So those are fairly large structures. But as we talk about these different structures, you may have noticed many of these structures have small elements. But why small elements? Wouldn't it be better to make them larger and then have less pieces? In some cases, yes, that's the case. That's what happens. But what we've come to realize after working in many countries is that there are some important attributes in each country that make for having different module sizes, we call them, the length of the pieces. So here's a structure being built where the pieces are about the length of a man, let's say 1.7 meters. We can go a little bigger, and here the pieces are somewhere around 3.2 meters. And we can go even bigger to pieces that are maybe 5 meters long. So how do we pick? How do we pick? It's really the economics of the particular location. How does this influence? Well, the defining characteristic, and there are many, but this is the most important, is labor costs. So if we have a country A where labor costs $5 a man-hour, you want to have short bars because you can optimize for material. You can make the structure lighter by having shorter bars. However, as the price of labor increases, country B, for example, at $30, then it's more balanced, the material and the labor to put it together. And if you go to an expensive country, country C, maybe it should be called country U, where maybe you're paying $100 per man-hour of subcontract price, then you must design a structure that has low labor cost or low labor input to install. And you can see that in country A, you will have the low-cost structure regardless because the labor costs to put it together are very small. But with the smaller bars, you get a lower cost structure. Whereas if you go to country U, I mean C, then your best bet is to have very long bars because then you reduce the labor to put it together. Of course, there's some limits to this. If you go to bars that are more than 6 meters, then they are difficult to transport. You have to have sub-spans to span for the cladding. And so this is just illustrative. You have to consider other parameters, but it gives you the idea of how labor impacts your equation. And it's not the same to build a dome in Bolivia as it is to build it in the United States. We design for the particular country and we optimize the structure for those conditions. One particular geometry that is very commonly used by our company is what we call the Saturn geometry. And this, regardless of whether we use short or long bars, reduces the labor. In a polyhedral geometry, we end up with quite a lot of different bars and different marks, we call them. The mark being the identification mark. So, for instance, in this case, you may get this type of repetition, but no more. And this is the red. If you go away from the mode, the most common, then you get less and less repetitions. So this creates complexity in putting the dome together. While the structure may be very efficient, it's difficult to assemble, or at least takes more man-hours. We came up with the Saturn geometry, which is inspired in the pattern of Saturn. So we have rings whereby 2 out of 3 bars are always the same. And not only that, the bars that are the same in the first ring are also the same as in the second ring, and so forth. So each ring is horizontal, providing for an easy way to reach the work front. And then there's no need for propping. We can actually design a structure to prop itself, and you get this type of repetition. All of the red bars are the same. So it makes for a very efficient build. And if you hold for, say, the length of bar, the number of bars are reduced compared to other common geometries, for example, the trapezoidal geometry on the right, and you end up with a lighter structure with less members, and all in all, a more efficient solution. So that's the Saturn geometry. Another all good type method that we've used is the lifting tower. So what is the lifting tower? Well, it's a device that allows us to have the workers work on the ground rather than on a 100 foot or 30 meters up in the air. This is the idea. There's an outer tower and an inner guide tower. And we have hydraulic jacks that push the tower up, raising with it the dome. Like this. And here's how that might work in the diagram. So all the time, new tools are being added at the bottom. Workers are safe. They are not exposed to the hazards of working at heights. Very first dome we did like this was a tough sell, but after it worked, then it's easy. And we only had the diagram, but now we have the actual photo. This is 120 meter diameter and about 50 meters at the apex. So, not only do you reduce the labor hours, but you also reduce the hazards and the risk. And that's always well received. Some other examples now of architectural structures. Some of you may recognize this building. It's not far from here. It's in Southampton Water, Marchwood to be specific. It's a 110 meter dome that we built for Veolia there in Southampton Water. We are told that the locals tell the tourists that this is where they keep the aliens. I don't know. It looks like it, doesn't it? This is a church in Mexico, funnel to heaven they call it, for obvious reasons. Notice the tube lengths there, very small in some cases, which is optimized for material because labor costs where this was built are very low. And the client wanted this beautiful shape. This is a project in Ghana. It's for another church, and it's 60 by 60 meters approximately, octagonal plan dome, not a regular octagon, but still. It's recognized in Ghana as the largest auditorium or something like this, and and it won some architectural awards. This is a gymnasium in Mexico. Interesting about this one is that it's clad with a wood deck and then a built-up roof. We also do space frames for architectural projects such as this aircraft terminal, or airport terminal rather. This is in Nigeria, in Abuja, and it's a freeform dome spanning 105 meters on the short direction and 228 in the long direction. So it's fairly large, built there on site. And this is a gymnasium, a velodrome, and it spans 80 by 120 meters, elliptical plan. This is an old building. This was actually done at the time of that very first conference. And it may have been in one of those papers, but this is from 1968 for the Olympics that were held in Mexico City. And my dad was involved in the construction of the hyperbolic paraboloids. At the time I wasn't able to give him a hard time about it because I know what was going on. But yeah, 1967 and 68. This project is in the Maldives. It's a mosque. And we had a bit of a disagreement in the office where people were actually punching each other to try and go supervise this particular job. Nobody wanted to go to the Maldives. These are the NEMAC domes. It's an interesting project because it's an industrial project, but it did have the characteristic that the client, NEMAC, auto parts manufacturer in Mexico, wanted it to have distinctive architecture. So they hired a renowned Mexican architect to design this, and they came up with this long freedom shape. And we ended up building 4 of these for the client. It's been very successful. They span 84 by 224 meters. Another architectural project is the Sumaya Museum in Mexico City. The Sumaya Museum is now an iconic building in Mexico. It has over 10,000 hexagons on the facade, and the location of each hexagon is given by a Geometrica joint behind it. This is how it looks. If you ever go to Mexico City, make sure you go there. It's really quite an amazing building. You've been there. No, I saw you nodding. But it's quite interesting. So, to achieve some of these buildings in different parts of the world is difficult. Because, as it happens, in our countries, and I'm talking about the US and the UK, and perhaps Europe in general, there's this idea that we shouldn't buy products from, or steel rather, and aluminum from China or some other low-cost countries, and there's these barriers. So that puts us at a tremendous disadvantage because other countries don't have these restrictions, particularly China, of course. So if we go to South America and we're trying to sell a building, they can compare us with Chinese produced space frames, and it's a very disadvantageous comparison. Because while steel tube in the US may cost $2 a kilo, in China it costs $1 a kilo. So even though our structures may be lighter and easier to put together, 100% difference sometimes in cost. It's hard to overcome. So how do we get around that, or how do we compete under those conditions? We came up with what we call the Hercules production line. And the Hercules production line is a transportable factory. This is how it looks when it's being used. This is how we make the tubes. But the trick is that the machine can be actually packaged and shipped around the world. So we've done this. We've actually shipped our machine to Taiwan and China to be able to do structures over there. We've also shipped it to Saudi Arabia, and to Nigeria, and to other places. And this gives us the advantage of sourcing to wherever it is less expensive and be able to compete with the locals or be able to compete with the world-class suppliers from anywhere in the world. We've even shipped the Hercules line by air. This is how it went to Jeddah. From Monterrey, where we have our factory, to Houston, and then to someplace in Labrador, and then someplace in Europe, I think that's Belgium, and then on to Jeddah. So we ship the factory, send it over there, and make it in Jeddah using Chinese tube. And that brings me to the Jeddah Superdome, which is one of our most recent projects and the world record in terms of geodesic dome. Longest span geodesic dome in the world. In December of 2019, we were approached by our client. At that time, they weren't yet our client. It's a Dutch company who said, look, we need to finish a 200-meter dome by May. I said, by May? Are you crazy? It was December. I said, if you gave me the order right now, I'd probably be getting tubes from my supplier by May. He said, look, it's going to get done. Do you want to be the one doing it or no? So we had to think about how to do it, and of course the Hercules line was the option. We ended up shipping the line over to Saudi Arabia. The dome was originally to be 200 meters, but when we told the client that if they just went to 210 meters, they will have the largest geodesic dome in the world, they decided to go to 210 meters. And now they claim to have the largest geodesic dome in the world. It started on these steel frames, tetrahedron, that support a ring beam at about 6 meters high. And we started assembling. And we went really happy for about 3 weeks assembling the first rings of the dome on the ground, so we would then lift them with the cranes. And then the pandemic hit. And everybody had to go home. Well, not quite. Apartments, rather. We had 12 people on site. They had about 100 workers to assemble the structure. But my team, Geometrica's team, had to go to their apartment for 2 months. Couldn't come out. Everybody was locked down. They were given the option to return home and maybe go back when the pandemic subsided, but our team decided to stick around because we didn't even know if there would be travel available at the time. So we stuck around, and in May we restarted the project. I lifted these pieces. They were 70 meters long, each weighing about 30 tons, with 2 cranes, and set them on the ring, connected them all together like this, and continued stick building with man lifts to complete the structure in what would have been the original schedule had it not been for the pandemic. But of course now they didn't need it for May because they couldn't hold the events they were going to hold in May, and they postponed everything 1 year. And so the building was eventually completed. This is blackout fabric, PVC fabric, with which they covered, and it's now, as I said, the largest geodesic dome in the world. It was finished and it opened the doors in June 9 of 2021. On the inside is how it looks. And another shot. So to give you a little bit of context, here's a comparison with other buildings of comparable size. The Astrodome in Houston is within half an hour from my home. Was the largest metal dome in the world for a few years. It spanned 30,000 square meters, and the weight of the roof was 2,500 metric tons, 83 kilos per square meter. And the Louisiana Superdome, which came just a little after that, spanning 207 meters, was also very close to the size of the Jeddah Superdome. It weighs also about 89 kilograms per square meter. The Jeddah Superdome was able to span the same distance for 40 kilos per square meter. So that's, you know, 30 or 40 years of technology there. And of course, you can't really compare, but the AT&T Stadium in Dallas, it's not a shell. And that's where the efficiency comes in the other buildings. When you have a hierarchical arrangement, a structural arrangement, you may you know, have the ability to open the building, but you won't have the membrane action that gives you the efficiency. So the weight is substantially more. So one last little show, it's a time lapse of the installation of a 107-meter dome with the Saturn geometry. This is the part most high-tech. Using the digital assembly tool, of course. That's it. That's it for the presentation. Thank you for listening. And any questions?
Thank you very much. Fascinating. You have lovely projects from all over the world. Just to remind you, in particular first-year students, you are going to deal with different geometries of spatial structures. You will learn how to generate the geometrical information for different configurations. So that is part of the practice for the configuration processing that we are going to do this semester. And one question that we pick up, you had a nice comparison between the self-weight of the structure in different situations. And when we are talking about the sustainability, we know that one of the key elements is reusing the material that we use. So how do you comment not only on the large span structures, so these are over 200 meters, probably in occasional situations we are going to have those, but what about different types of spans and what are the comparisons with different types?
Well, good question, thank you. There are several parameters. We are able to reduce weight of the structures, but as we saw earlier, it's not always the weight that governs the economics. Mind you, yes, you're saving carbon if you reduce the weight. However, because we value the labor so highly in some countries, you need to put a little bit more material in order to reduce the labor component. So whether it's good or bad, I don't know, but usually economics drives what you end up doing, particularly in the industrial and agricultural projects.
Excellent. Thank you. Any questions from the audience?
Please.
Could you briefly me explain your design process? So if you're given some weird shape of dome, how do you tackle that?
Well, usually the design is included in our proposal. So there is a back and forth with the client before we get an order, and it has to be very efficient because we don't have the resources to walk the client through a design. So we often have to use parameters from previous experiences to price a project. Sometimes, if the structure is very, very complex, we will offer an engineering scope to start. But then, when we have an order, then the design again enters into a second stage where we back and forth with the client. We send them a layout first for their approval, where we already represent the geometry, boundary conditions, loading, and all that. When they approve that, then we proceed with the detailed design, from where we can produce what we call order requisitions or material requisitions, and then make the structure. So that's the process. It's 3 stages. First, before the order, a very small preliminary engineering. Then after the order, the basic engineering for approval, then the detailed engineering for production.
Okay.
Excellent. Okay, yes please.
One more question.
Yes,
Thank you very much for the presentation. I haven't been here from the very beginning, but I'd like to ask one thing, because I see it's a special type of structures you're doing here. What happens with regard to structural redundancy? For example, if a connection fails or a member fails, what happens? Are you having any kind, how are you managing any kind of the potential and the risk of any kind of catastrophic failures?
Yes. There is a risk of catastrophic failure. The structures are very sensitive to imperfections, particularly when you get into the long span domes. They're sensitive to changes in the loads. So what we have to do is apply appropriate overload conditions, material safety factors, all of the things that you would do to do a conservative engineering proportional to the risk and the consequences of your mode of failure. While a joint may fail, there is for a particular individual joint a great degree of redundancy. So because if you have a very local failure, generally in a roof you won't have anywhere close to the design loads. So it's a low risk type, and it happens quite often in the mining industry because they'll have a truck drive onto the dome, sometimes through the dome. I kid you not, that has happened. And then the structure doesn't collapse because you do have that redundancy and that overload for the 500-700 year return period on the wind or whatever it is for the snow. But where you don't have a whole lot of redundancy is for, say, large snow if you have a very shallow dome. So you have to have appropriate overload factors, appropriate buckling factors, and to be fair, the codes don't give you guidance for that. That has to be, you know, something that we provide for. But we do, we have to consider it.
Thanks very much.
You're welcome. Yes, sir.
You mentioned putting PVC fabric on top of the domes. I just wanted to ask, what is it about the properties of the fabric that protects it against, for example, the elements, different weather conditions, that kind of thing?
So the PVC fabric is a very popular architectural fabric, but there are others. They're silicone-based, they are Teflon-based, ETFE or whatever they're called. And there's also film that you can use. So any of these can be adapted. The PVC has the huge advantage of cost. And it has now fantastic durability, which wasn't the case 20 years ago. But now they do have very good fabrics with that base.